In this lecture, I am going to discuss the effect of dielectric on capacitance. In the last lecture, I told you that capacitance depends upon several factors. One factor is shape of the plate, and in the last lecture I explained about how shape determines capacitance. In this lecture, another parameter which capacitance depends is dielectric, which we discussed in the previous one. So in this one I am going to discuss about the effect of dielectric on capacitance. In order to explain that, we are considering the case of parallel plate capacitor, because we already discussed about parallel plate capacitor. So this discussion is purely for parallel plate capacitor, how a dielectric will change the capacitance of a parallel plate capacitor. That is what we are going to discuss. So for that, let us consider a parallel plate capacitor. This is our parallel plate capacitor. Two parallel plates are there. This is P1 and this is P2. In the previous discussion, what we explained is, in between P1 and P2 there will be air. Okay, now instead of air, let us consider some other dielectric. Other than air, let us consider some other dielectric in between. So let us consider a dielectric in between the plates. A dielectric material we are considering, some dielectric. We are not specifying the material. Some dielectric is placed in between. This is dielectric. Okay, we are having two plates. One is P1 and another is P2, and in between P1 and P2 we are placing a dielectric. Okay, when you connect this battery, this plate to battery, when dielectric is not there, let us say that there is an electric field from P1 to P2. If P1 is positively charged and P2 is negatively charged, there is an electric field, an external applied electric field E0. Now you can see that E0 is acting in this direction, because electric field will be always acting from positive to negative, isn't it? Now you are placing your dielectric in this electric field. You are placing your dielectric in this E0 electric field. When you are placing your dielectric in this electric field, what actually happens? Dielectric means it is also a material. There will be electrons. So you are placing that material, dielectric material, in an electric field, and in that case the electrons in the dielectric will get attracted towards the positive plate, isn't it? Because electrons are negatively charged. So electrons in the dielectric will get attracted towards the positively charged plate. When electrons are getting attracted towards the positively charged plate, all the electrons will accumulate near to the positively charged plate. So what actually happens is, all the electrons in your material will move and will reach here. I am using negative sign to represent electrons. So all the electrons will come near to the positively charged plate, and the atomic cores, that means electrons are coming out they are negatively charged, and positively charged will move towards this side. It is actually atomic cores. We will simply represent it by sign. So positive charges will move towards the negative plate, and the negative charges will move towards the positive plate when you place the dielectric in this field. Now you can see there is a charge separation inside the dielectric. When you kept the dielectric in an external electric field, there is a charge separation in the dielectric, isn't it? Negative charges are on one side and positive charges are on the other side. So there will be an electric field because charges are separated. Now there will be an electric field from positive to negative in the material, isn't it? From positive to negative, because electric field is always from positive to negative. So this will be the direction of electric field in the material from positive to negative. This is actually an induced electric field, because when you place it in a field, there is a field induced because charges are moving in that field. So this is an induced electric field. We will represent it by E induced. Okay, so E0 is in this direction and E induced is in the opposite direction, isn't it? So what is the net field? E net is equal to E0 minus E induced. Please remember that E0 will be always greater than E induced, because your external field will be always more. Internal field or induced field cannot exceed your external field. So E0 will be always greater than E induced. That is why we are taking it as E0 minus E induced. Now the same situation we can represent it in another way. If you are not keeping any dielectric material, then whatever be the field you are applying, that will be the field in between the plates. That means E0. Okay, if dielectric is absent, the field between P1 and P2 will be E0. But you are placing a dielectric of dielectric constant. That dielectric is having a dielectric constant K. Let it be K, capital K. You are placing a material and its dielectric constant is K. When you place it, the net field in between the plates reduces, isn't it? Now it is not E0, it is E0 minus E induced, which will be less than E0. So you can say that when you place a dielectric, the initially applied field reduces by some amount. Initially it is E0. Now when you place a dielectric, it will become E0 minus E induced. That means initially E0, now it is less than E0. How much it will reduce? It is by a factor of K, that is dielectric constant. So this will be same as E0 by K. It means your E0 reduces to some extent. How much? By K amount. It reduces by K amount, which is same as E0 minus E in. If you find E0 minus E in, that will be equal to E0 by K. Okay, now I am not using the vector sign, I just need the magnitude only. So I am just writing the magnitude alone. Now this will be the electric field in between the plates, E0 by K. Now you know the relationship between potential and electric field. Potential is equal to electric field into separation. Let it be D, separation between the plates. Initially we consider that it is D. Now also let us consider that this separation between the plates is D. So potential between the plates is nothing but applied field into D, isn't it? Here what is the effective field? It is E0 by K. It is not E0, it is E0 by K. Field experiencing in between the plates is now E0 by K into separation is D. Okay, so this is the potential. Now our intention is to find capacitance. What is capacitance? C is equal to Q by V. And we already explained, if the surface charge density is sigma, that is in unit area, if sigma charge is there, then in total area there will be sigma into A charges. So Q is equal to sigma A. We explained in the first chapter, and we used the same thing in the last discussion also. So Q is equal to sigma A. Now V, what is V? E0 D by K, isn't it? So you got C is equal to sigma A divided by E0 D by K. This is what you got, E0 D by K. Now you know what is E0. E0 is the actual field in between if dielectric is not there, or we can say in air. And you know that E0 value between two metal plates, we applied Gauss's theorem in the first chapter, and you got it as sigma by epsilon 0 between the plates. So E0 is sigma by epsilon 0. Then D by K is there, isn't it? Now you can see that your sigma will get cancelled with this sigma, and epsilon 0 will move to numerator, K will move to numerator. So what you will get? You will get epsilon 0 Ka by D, or you can write it as K into epsilon 0 A by D. This is C. Now if you check this one, when there is air in between the plates, you got the capacitance as epsilon 0 A by D for a parallel plate capacitor, isn't it? Now we are going to find the capacitance when you place a dielectric in between, and you can see that along with that factor epsilon 0 A by D, you are actually having one more K. That is the only difference with the previous one. So if you take it as C0, C0 means without a dielectric, then this can be written as C0, isn't it? So you can write C is equal to K into C0. What does it mean? When there is no dielectric present, or only air is present in between, if capacitance is C0, now if you insert a dielectric constant K, you can see that capacitance actually increases, because you are multiplying initial capacitance with K. K will be always greater than 1, because any dielectric will have a dielectric constant more than 1. So you are multiplying your C0 with K, means this C will be more than C0. That means capacitance increases when you place a dielectric in between. Okay, so this is the effect of dielectric on capacitance. When you place a dielectric in between the metal plates, its capacitance will increase by a factor of K, where K is nothing but the dielectric constant. So you can define K as C by C0. So you can say that K is the ratio of capacitance when a dielectric is placed with the capacitance when air is present, provided that the distance between the plates remains same. Okay, which means if you have two plates and initially let air be the medium in between, dielectric medium, let it be D. If C0 is the capacitance, now you will place some dielectric in between and you measure the capacitance, it is C. Then you can calculate the dielectric constant of that material which you placed there by simply finding C by C0. This will give you the dielectric constant of that material. And for different material, dielectric constant will be different. When dielectric constant increases, that means if you use a material with high dielectric constant, then capacitance will also be greater. This is the relationship between dielectric constant and capacitance. When you place a dielectric in between the metal plates of a capacitor, you can increase capacitance. So example for dielectric materials are paper, then water, then mica. Like that, any material you can place. In all these cases, you can increase capacitance. Okay, normally we will use paper, mica, etc. in between the two metal plates in capacitors in order to increase their capacitance. Now, in the next lecture, I will change this situation. Instead of filling a dielectric in the entire space, I will keep it only in a small region and the rest of the region will be empty, and I will find the capacitance in that case also by inserting a thin slab, not in the entire space in between the plates but only in a small region. I will place a thin slab and I will find capacitance in that case also. That is again a dielectric slab, but it is not filling the entire region, it is only in a small region in that gap.